Let's try a two-dimensional problem involving point charges. We'd like to find the vector electric field that's created at the origin. Note that the particle at the origin cannot contribute to the field at the origin. Only the other two particles can. So let's start with that. We have a positive 6 nanocoulomb charge on the right. And we have a negative 3 nanocoulomb charge on the bottom here. I'll call that one Q3. And I'll write point P here to show the location where we want to evaluate the field. In order to do this, we need to know the physical distance from point P to all of the charges around it. So we need to know this distance here. I'll call that R. And we need to know this distance. This can be R3. All right, we want to consider what the signs of the charges are. That's important. This one's a positive charge and the other is a negative charge. And at this point, you want to imagine, what if there was a positive test charge at the origin? How would the charges around it push or pull on that test charge? That's going to be the direction of the field contributions. So positives are repelled by other positives. That means that there will be a contribution from Q, which points to the left. But positives are attracted to negatives, which means there'll be a contribution to the field due to Q3 that points downward. Now, just to make things a little bit more clear, I'm going to add a 2 onto this charge so that it doesn't get confusing. We'll call the charge at the origin Q1. But that doesn't even play a part when it comes to calculating the field at the origin. Now that I have those assignments, I'll call this E3, and this one can be E2. See, each of the charges makes their own contribution to the total field. Okay, so let's get started. What we want to do here is we want to sum the two contributions to find the total field. So it's going to be E2 plus E3. We want to replace the E's with their formulas. And the formula for field is K Q over R squared. And as I had done in previous videos, I want to add a direction to it as well because it's a vector. That'll be R2 hat. And we'll have K Q3 over R3 squared, R3 hat. Now, a lot of times when people are first starting out with this, they may be not too confident about how to deal with R hat. If that's the case, you can assign your own direction to it based on what you've drawn in your picture. Now, to the right is our positive X direction, and up is our positive Y direction. So that means I already know that E3 is going to be in the negative J hat direction, and E2 is going to be in the negative I hat direction. If I want to use that knowledge here, and I can just write K times the absolute value of Q2, and then we'll just put the direction that we see in the picture, negative I hat. I can do the same thing for Q3. And it's in the negative J hat direction. All right, let me fill in the numbers. We'll get an answer that way, and then I'll also show a more advanced way to do it as well. Okay, that's what I have so far. Let's plug it into a calculator now. Okay, there's our result. The field points to the left and down. Let's say, though, that we tried it a different way. If we use the formula without absolute value and use the R hats this time, how would it look different? Well, first we'd have to identify what the R hats are. R2 hat will point from the charge exerting a field toward the point where we're evaluating the field. This is going to be R2 hat. Notice that it is equal to negative I hat. And then we have R3 hat. Notice that R3 hat is equal to J hat. I hat points to the right, J hat points up. So that means that negative J hat points down and negative I hat points to the left. Now what we can do is we can replace the R hats with what we had just found. And when we introduce the charges, we actually keep their original signs. If we did it correct, we get the same answer as we had gotten doing it the other way. And it works. So our electric field points to the left and down. Now when you're asked to find the total electric field, this is vector form, and that gives us all the information we need. But you might also have to go farther and find the magnitude of it. When that happens, we want to use a formula from Physics 1 where we take the square root of the squares of the components. So the one on the left is EX. And the one on the right, attached to J, will be EY. We want to now plug those in so that we can figure out exactly how long is this resultant vector, which is called E total. To find E total, you just make a rectangle here out of the components. Go from the place where they're connected at their tails, and then go to the other opposite side of the rectangle. And that's going to be the length that we're looking for when we do this formula. It's based on Pythagorean theorem and the distance formula in math. So let's see, we're going to have 600 squared negative 2700 squared, 2770 approximately. And notice it doesn't have a direction anymore because it's just a size. It's a magnitude. You might also be asked to find the angle in standard position of that E total. To do that, it's a review from Physics 1 here. If you want a more in-depth explanation of this, just see my Physics 1 playlist from the past. But what we need is a reference angle. And that is found with the formula tangent inverse of EY over EX. However, we always use absolute value in this formula. Don't want to put any negatives into it because we're just getting a reference angle between 0 and 90 out of it. Comes out to 77 degrees or so. And that is not the standard position angle yet, because when we're in quadrant 1, the standard position angle is the reference angle. If we're in quadrant 2, then the standard position angle will be 180 minus the reference angle. In quadrant 3, this is the one that we're actually in, we want to do 180 plus our reference angle. And in quadrant 4, we do 360 minus the reference angle. The idea being that our vectors could point in any of these 4 directions, as long as they're not on the axes themselves, of course. And our reference angle is going to be the angle it makes with the x-axis. Okay, so our 77 is actually this here. We want standard position though, which goes from the positive x direction all the way around, and we get an angle that's greater than 180 here. Our standard position angle, therefore, is about 257 degrees. That'll do it.